I'd just like to thank Shane for inviting me to present on this research today. And hello everyone, it's great to see everyone in person after all these online seminars. I'm a bit over it. I'll be presenting the research I conducted to attain my PhD in arboriculture, and my title for this research was Soil Compaction Affects the Growth and Establishment of Street Trees in Urban Melbourne. So I'd like to start by outlining why this research was necessary. We all know that urban nature strips can be a hostile growing environment for street trees, and this can range from planting trees in new developments, where it's highly likely the soil profile is altered from site cuts to fill soil. The soil may even be compacted by construction vehicles and later by parked vehicles, and here are some examples that I only took a few weeks ago. Often nature strips are narrow with underground services competing for vital root growth area as well. There are also constraints for planting trees in established urban areas, often if the soil has not been ameliorated over time, and the soil can remain compacted when planting into the nature strip. It can be costly and time-consuming to ameliorate compacted soils, and some methods may not be viable due to the risk of damaging those underground services. I wanted to conduct the research to determine a range of species which would tolerate and establish more successfully in compacted soils, and this would mean that amelioration of the soil wouldn't be necessary and the species would have more characteristics to survive to the harsh urban conditions. So I'll just start briefly with what is soil compaction. A lot of you would already know, but it can be a little bit of a refresher. So compaction is the degree to which soil particles are packed together. The organic bonds holding the soil structure together are broken and the soil particles are pushed together, filling in that pore space. The micropore and macropore space for water and air is reduced or can be lost altogether by slowing the infiltration rate and slowing the soil's ability to drain quickly. Roots also must push harder through that soil, and compaction usually occurs in the upper 15 centimetres of the soil, directly affecting that root zone, and it can vary over short distances and to a wide depth. So how is it measured? One method is bulk density, which is calculating the soil's dry weight divided by its volume, expressed in megagrams per cubic metre. And this photo shows the coring method, which I used in my experiment, where a sample of undisturbed soil is taken, then dried in an oven for 24 hours, dividing the weight by the volume. This diagram shows in red the root limiting bulk density, readings depending on soil type. So a sandy loam here is around 1.65. Another method is penetrative resistance, which is the ability of a soil to resist physical penetration by an object or root. This photo shows a cone penetrometer, where a metal probe is pushed into the soil and it instantly measures the compaction level in megapascals. A limitation with this method is that the readings are susceptible to soil moisture and soil type. For example, if a soil with low compaction, when dry, could have a high resistance reading, and a compacted fine-grained soil, when saturated, could have a low reading. So for this method, a sandy loam with a root-limiting compaction can measure about 2 MPa. So the effects of soil compaction on establishing trees can be shown in this diagram. The roots can be often confined to the planting hole. There is limited root establishment into the surrounding soil, and the planting hole can be waterlogged. And this can result in death or poor root establishment and canopy growth. There's also effects of compaction on established trees. So when roots encounter the compacted soil, they generally grow parallel to or away from the compacted zone, but growth may slow or stop. If the lateral roots can fit through the pores of compacted soil, then the root growth continues while the main axis of the root is constrained. And this can result in increased branching and radial thickening of the roots, which can then exert a greater force through that compacted soil. Trees growing in compacted soil tend to have a spreading root system and often less than 10 centimetres deep. Species with the high root-shoot ratios have greater ability to penetrate the compacted soil. So now to the experiment, which is the fun part. So I hypothesised that since bulk density of compacted soil compared to uncompacted soil was root growth limiting, species would then have a reduced growth in compacted soils. The experiment investigated whether there were differences in canopy and root growth, root length, and soil compaction over time. Comparisons were made between species growing in compacted and uncompacted soils. So the experiment took place at Melbourne University Burnley campus, and I'll use the mouse. So here I'm showing the large block, and here is the smaller block. So the larger block measured 120 metres long by 12 metres wide, and there were 10 individual blocks within that larger block. The second area was 75 metres long by 12 metres wide, and there were 6 blocks located in this smaller area. And each individual block measured 12 metres long by 5.5 metres wide. So there were 16 individual blocks altogether. 8 were compacted and 8 uncompacted. The species can be shown on the screen. I won't read them out. These were all included in the growth trial, and they're a mixture of Australian natives and exotic. And there were a total of 128 trees. So here I'm showing the diagram of the block layout within the large block and the small block, and it shows the compacted area in the orange and the uncompacted in the blue, and each letter represents the different species. And the block's treatment and the species were randomly selected. So the blocks were prepared by scraping the existing turf with a bobcat. Then all blocks were ripped to a depth of 800 millimetres at 400 millimetre intervals. Here you can see that the treatment of some uncompacted blocks and compacted blocks. So the smooth area is the compacted block, so there's 3 in that area. The one on the top left is uncompacted and the rest are uncompacted. And the compaction was done using a vibrating ride-on roller, similar to what they do roads with. The bulk density of the soil was tested for all blocks to determine the level of soil compaction prior to planting, and then mixed particle mulch, so council-type mulch, was then spread over the surface of each block to a depth of 75 millimetre. So here's an example of the photos. So each tree was photographed prior to planting, with if the potting mix wasn't too loose, with the pot removed to see the extent of the root system. So this is an example of the eucalyptus. And then the trees were photographed at the time of planting and at 2 monthly intervals after they were planted. So now to the growth trial. The trees were grown for 20 months. During that time they were staked, weed control, hand watered and mulch top up. And then every 2 months, the height, canopy width and trunk diameter was also measured along with that photograph. So I'll just show a series of slides now, one for each species. So this is after the 20-month period. So this is an example of the Alocasia, really poor. Each slide shows the poor growing specimen on the far side, and the side closest to me is an example of the well-grown specimen. And you'll note at the bottom it might have compacted or uncompacted at the bottom. So in this case, the example for the Alocasia, the worst specimen was in compacted soil and the best specimen was in uncompacted soil. So for Corimbia, the worst specimen, you can see there's quite a lot of dieback. That was in uncompacted soil. And the best specimen was in compacted soil, and that had a height of 454 centimetres. So for the Cupressus, the worst specimen was in compacted soil, and the best specimen was in uncompacted soil, and that grew almost 3 metres. So for the eucalyptus, it tended to have quite a wide canopy width for most of the specimens, rather than tall. So again, the best specimen was in compacted soil. So for the Lophostomen, the worst specimen that had a lot of basal shoots was pretty struggling, and that was in compacted soil. The better quality specimen, again, had quite a wide canopy. That was in uncompacted soil. And for the olive, the specimen that struggled was in compacted soil. Again, quite a wide, bushy specimens for most of the trees that were planted. The better one was in uncompacted soil. For Quercus, it's a bit hard to see the initial photos. These were planted bare root. So I actually had to use blue tack to stick them to the ruler. So the uncompacted, again, just a lot of basal shoots, didn't grow that well, but the better specimen was in compacted soil. Waterhousia, so the last species, the poor growing specimen, again, had a bit of dieback on the main terminal leaders. That was in compacted, but the better specimen, again, quite wide and bushy, uncompacted. So now, after the 20 months, after looking after all these trees, I did penetrometer readings. They were taken several locations for each block, and soil samples were taken to measure the bulk density. And that's, again, that same photo showing that coring method that I used. So the canopies are removed at ground level, and I had to cut them up, put them in big paper bags, and then dry them in big industrial ovens until their weight stabilised. And the root systems, we excavated them using an air knife and then sensitively lifted them, and then they were oven dried again till their weight stabilised. Now to the results of the experiment. So the mean bulk densities for the uncompacted blocks for the initial and final tests were 1.5, which is shown here. And for the compacted blocks, the initial tests were 1.88 and the final tests were 1.6, which is shown over here. So there was a significant difference between the uncompacted and compacted sites, which was maintained for the duration of the experiment. Therefore, even though the level of soil compaction reduced over time, it was still classed as compacted and was significantly different to the bulk density of the uncompacted soil. And as stated earlier, with root limiting compaction, can measure 1.65. For the penetrative resistance data, and that's shown at the side closest to me, there was significant difference in treatments between the initial and the final tests. The resistance of the compacted soil, being 2.95, was significantly greater than that of the uncompacted soil, 2.09. As stated earlier, it's considered root limiting above 2 MPa. The penetrative resistance results also show bulk density readings, a more accurate representation of soil compaction, as it shows that penetrative resistance actually increased in compaction over the final readings, where the compaction levels reduced over time using the bulk density method. So that was an interesting outcome. So I'll just run through, there's a few graphs to follow, but they're laid out in a similar fashion. So the mean is on top of the bars of the graph, and it's showing over the 20-month growth period for each of the graphs. And if there's a letter on top of each of the numbers, on, say, for example, the lophostomen, that shows that there's a significant difference between each treatment. So for eucalyptus, A and shown by the A and the B, they were significantly taller in compacted soil. Oh, sorry, I'm on the wrong one. Sorry. So for this one, the trunk diameter, the lophostomen, shown by the A and the B, and the olive, shown by the C and the D, had significantly larger trunk diameters in uncompacted soil. And the eucalypt had the largest trunk diameter, followed by the corymbia, but they weren't significantly different. So for the tree height, the eucalyptus, shown by the A and the B, was significantly taller in compacted soil. The other species weren't significantly different in height between treatments. So for canopy width, the olive, shown by the A and the B, was significantly wider in uncompacted soil, and the mean full canopy width was greater for uncompacted versus compacted soil in all species apart from the Alicasuarina. That was another interesting finding, that they were wider in the compacted soil. So for root length, Alicasuarina had the shortest overall root length of 441. So I'm looking at this mean here in this column. And that was well below the shortest root length for Quercus at 768 mil. Eucalyptus had the longest overall root length of 2,166 mil, followed by Cupressus at 1,454 mil. Several species had longer roots on average in compacted soil. So we're on this column here. These were corymbia with a difference of 302 millimetres, Cupressus difference of 40 mil, and eucalyptus with a difference of 90. Olea had the largest difference in root length between treatments of 355 millimetre in uncompacted soil. So for the dry weights of the canopies, an analysis was done to determine if there was a significant treatment effect within the species, and it's summarised in this table, and only Lophostomen and olive showed a significant treatment effect on canopy dry weight, and in both cases they were significantly higher in uncompacted soil. So the root dry weights, olive was the only species which had a significant difference between treatments. So this is showing where the roots were significantly heavier in uncompacted soil for the olive, and Corymbia was the only species to have a heavier roots in compacted soil, although the difference was not significant. So, for the discussion regarding the trees, the eucalyptus and Corymbia had the highest readings for each of the 5 measurements, which were the tree height, canopy spread, trunk diameter, canopy mass and root mass. And they all grew well in compacted and uncompacted soil. Corymbia, Lophostomen, Olea, Quercus and eucalypt were all significantly taller in the compacted soil. The tallest growing species of was eucalyptus, while Lophostomen was the shortest, with Corymbia, Olea and Quercus ranging in between. This impacts street tree selection, as rapid height growth might be considered desirable, and if so, eucalyptus would be a preferred species choice in that scenario. Corymbia, Cupressus, eucalyptus, Lophostomen and Quercus had significantly higher, larger canopy mass means compared with root means in the compacted soil, suggesting that compacted soil had a negative impact on root growth. And Quercus had a greater mass below than above ground in compacted and uncompacted soil, so that was another interesting discovery. The soil discussion. So to gain an accurate measure of site bulk density data was collected from the undisturbed soil profile, which is where the root growth would occur during the tree establishment. The bulk density and penetrative resistance data verified that there were significantly different levels of compaction between the 2 treatments. But over the 20 months, the bulk density of the uncompacted soil remained constant, while that of the compacted soil reduced. From this information, it's possible that root penetration reduced bulk density, but it's well known that mulch can be a cost-effective remedy to soil compaction over the medium to long term. But this study supported this approach, but over a possible shorter period of 20 months. You can have that good effect of reducing soil compaction just by using mulch. Now to the conclusion. So after the analysis, the 8 species were placed into 3 categories. So category 1 was Corymbia and eucalyptus. They increased growth in compacted soil, were more tolerant of soil compaction, and may not require soil amelioration prior to planting. For category 2, Cupressus, Quercus, Waterhousea, they had growth unaffected by soil compaction, were tolerant of soil compaction, but may benefit from site amelioration to alleviate this soil compaction to ensure their optimum growth. They will grow adequately if the soil remains compacted. And for category 3, the Alicasuarina, Lophostomen and Olea all had reduced growth in compacted soil, did not tolerate soil compaction, and site amelioration would be necessary for growth. These species may not be suitable for compacted soils. I'd just like to acknowledge Melbourne University for supporting my PhD and my research. Also to my supervisors, Dr. Greg Moore and Dr. Peter May, for their huge support along the way. And if you'd like to learn more about my research, it's been published in the Landscape Below Ground number 4, which is an ISA publication, and also in the Journal of Arboriculture and Urban Forestry, which is a more condensed content from the book. Thanks for your time, and I'll answer any questions.
How deep was the compaction? I saw that machine going over the top. How did you measure the depth of the compaction?
Yeah, so with that soil corer, I then dissected that into 3 lots, so 10 centimetres, so it was 30 centimetres in total, and then I did 3 lots of that. So it was mainly within that top 10 centimetres, gradually reduced within the 10 to 20, and then it was less compacted within the 20 to 30.
Okay, so do you think the difference was oxygen levels, water levels, or compaction? There are 3 things there, isn't there? The oxygen
Yep.
levels in that top level, or whether it was less water to those trees, or because of the compaction
Yeah.
wasn't improved?
With most compaction, it's a combination of all of that. The degree of compaction will affect the ability for the water and air to infiltrate within the soil. Yeah.
Were you surprised by your results?
Yes, especially the eucalyptus and corymbia, that they actually grew a lot better in the compacted soil. But then I was surprised with the quercus because they typically like swamp type conditions in their natural environment, which is often, that can mimic the conditions of compacted soil, that they didn't grow as well as those 2 species.
I have a question from Miss Moore, and just for the recording, you can just repeat your question a little bit.
Yep.
Thanks for your presentation. With your 3 categories that you grouped your trees into, were there any sort of drought resilience or root features that united them, that meant that they were grouped, like a reason that they were grouped, I guess?
It was a combination in the root growth and the canopy growth.
Right.
So all of, like, with the material that I've presented today, there was a whole lot more that I didn't include, that I did do testing and etc. So it was all a combination of all of those results, and what was significant, some might have been higher than the other, but they weren't significant. So it was sort of a combination of lots of factors.
Thanks.
Mr. Stokes?
Just wondering, do you think that, obviously I think it was touched on, that waterlogging may have impacted some of the trees, and that's why maybe some species like the eucalyptus plantamus did better in the compacted soil because they didn't get quite as much moisture? And if so, would that change, like, depending on the seasons and like area that it's growing in? Do you reckon that would obviously impact?
It might have had some impact, but with the experiment having them growing in pretty similar conditions, even though there were 2 separate blocks and different blocks, there would be that variability, especially on that site that they were grown in. There's been lots of experiments and development done on that site in the past, so we just tried to make it as uniform as possible.
And in the centre, yeah.
Why do you think the eucalyptus and corymbia did better in compacted soil, like based on your research? Is it an evolutionary trait or something else?
I'm not sure about that one. Yeah, so just from having, so it could have been provenance as well of where that that stock came from. That's a whole lot of other research as well, because we also know, especially with Lophostomen, there can be ones that are quite tolerant of the dry conditions, but then there are some others that aren't. That just depends on where that seed stock was sourced in Queensland.
And one last one from Perth.
The
it was a little bit difficult seeing we were excavating, so we were exposing all the roots, and then it was sensitively excavated up. So I looked a little bit at root depth, but because they were lifted, it was mainly once they were suspended, what could we see that might have been at depth. But I also did measurements on the amount of growth in the north, south, east and west of those roots, and one of those outcomes was that most of the roots grew more on the north, and we assumed it was more so because of the warmer soil within that area. So there's a lot of little findings that are all through the research as well.
And we'll have one more question with a quick answer.
Is there any pathogen testing pre or post in the soil?
So no, I didn't do any soil pathogen. There were some pathogens that affected the canopy, so I just used pyrethrum type spray.
It'd be interesting if the compaction, if something was present, whether it was influencing growth.
Yeah.
Okay, thank you, Dr. Alicia Fitzgerald.